Welcome to Lesson 8A, Room with Unsteady Coefficients. We're going to look at room ventilation again, but this time with unsteady coefficients. We still have the same geometry that we had before, but we're going to allow some of these parameters to be functions of time rather than constant. So we're still going to consider, as before, well mixed, and this is dilution ventilation in a room. So we're not talking about displacement ventilation. We have well mixed conditions. So we have this ceiling fan to represent that, and we have a source, and we're going to do exactly the same thing we did before. However, for the general case, this Q can be a function of time. This S can be a function of time, the source. This Q, of course, is the same Q as a function of time. CA can be a function of time. Of course, C is always a function of time. We're not going to let volume be a function of time because it's always fixed for a room, although I suppose you could do that too. But we are always going to assume, as we did before, that S is small enough that it doesn't change the overall Q. We're adding some vapor into the room, but it doesn't change significantly the Q. So Q coming in is the same as Q coming out like before. It's just that these are now functions of time, whereas previously we had S, CA, Q all being constants. So we have the same equation as before, but now we have non-constant coefficients. C, of course, is always a function of time because that's what's exponentially growing or decaying in a simple room ventilation. So the geometry is the same as before. The equation is the same as before. We just have these non-constant coefficients. So mathematically, it's still first order.
How do we know it's first order?
Well, there's only one derivative. There's not a d squared, dt squared term, so it's first order. And it's still an ODE because this is only a function of one variable, time. It's not a partial differential equation. It's a first order ODE with non-constant coefficients. Now, you may have studied this in your math class. I assume they still do that. I remember doing this when I was a sophomore or something in college way back when. And we looked at some simple cases of first order ODEs with non-constant coefficients, like some kind of polynomials and stuff. So for certain cases, this can be solved analytically for some limited cases, but usually we'll have to solve numerically. And I can tell you in advance, we've already done this with the Runge-Kutta technique previously, so we'll be able to use that again. So let's look at how to solve this kind of equation. There's two types of unsteady problems that we'll discuss here. Number one, piecewise. And what we mean by that is all or some parameters change in piecewise fashion. They vary with each segment of time or each piece. We already did this. Recall back when we talked about mass body burden, MBB, for a worker that arrives at work with no concentration of the chemical in his body, and then he starts heading towards some steady state value, say for the workday, but then here he goes home. So his mass body burden starts to tend towards zero. So the steady state value would be zero, but at some point he comes back to work, and at that point he'll start growing exponentially again. And we kept doing that for Monday, Tuesday, Wednesday, etc. So you remember those kind of problems. This is identical because in this kind of a problem, what's nice is that for each time segment, we have an analytical, which is exact solution. So we just have to start with MBB 0, and then we set MBB 0 reset to this value when we start doing this second one, and then we reset it here again to start doing this one. And so you can do that in piecewise fashion. Number two is the general unsteady case. Parameters are functions of time. We can use some numerical technique. I'm going to use only Runge-Kutta to solve this numerically. And I've already done that previously and showed you some simple examples in an Excel spreadsheet in a MATLAB file. Let's do some examples of each of these. So let's start with the piecewise case. This is actually example 5.4 in the text. A conference room with 100% makeup air. We'll talk about makeup air later. Just for now, this is a simple ventilation that we're talking about. And it's the same diagram that we had up here. We bring fresh air in, we take the exhaust air out. In this case, we have more than one source. So in this case, we're talking about smokers. We have a conference room here, volume given. Contains 6 people who smoke at irregular times over a 90-minute period. So this is the number of smokers. So 0 to 10 minutes, 2 people are smoking, 10 to 20 minutes, 4 people are smoking, then nobody's smoking, then 6 are smoking. You get the idea. We have different numbers of people smoking. This is exactly the kind of problem that we will treat as a piecewise problem. And that's because Q, S, CSS, CA, ambient, and C naught equal constants in each segment. Now, some of these change between different segments, namely S is going to change with segment because you have 2 people smoking, 4 people smoking. Therefore, CSS will change too because you have more or less source being added. In this problem, Q stays the same, CA stays the same, but you have to be careful with this one, C naught. Originally, you might not have any smoke in the room. However, every segment, you have to reset the C naught for each segment. This was apparent here when we did the MBB, we did the same thing because you're going along with this analytical solution, this exponential equation, till you get here. And now we kind of pretend we're back at t equals 0. We're starting a brand new problem with this MBB 0 at time t equals 0. We'll call this like another t equals 0, a brand new problem with different conditions. So we do exactly the same thing here. Here we have smoke particles. We're going to assume that the particles move with the air. So they're very small particles. Let's treat these smoke particles as a gas. This is 1,100 micrograms of these particles per cigarette, per smoker. So when you have 2, you're going to multiply that by 2. So that'll be our source strength. We give the volume flow rate, and that's a constant. We have no recirculated air, as I said before. The initial smoke concentration in the room is not 0, but it's 20 microgram per meter cubed. And the ambient air also has some smoke from the ventilation system. We just set both of those to 20. Assuming well-mixed conditions, compute and plot smoke concentration as a function of time for this 90-minute period. These times are in minutes. And also compute the maximum concentration and the average and compare with the standards. Here's one of the standards, 3,000 microgram per meter cubed for these particles. So how do we solve this? I used Excel, splitting the time into 6 different time periods. And then I also have this Excel file available to you on the course website. At each time, we're going to march in time. We calculate C of t from our analytical solution, which I gave last time. That was the equation we had, and simply solve this for C of t. So at any time t within a segment, because as soon as you change the segment, you're going to change your CSS and you're going to change your A. That'll change too. This equation is for constant coefficients within the segment, but the properties will change when you go to the next segment. So you got to be careful to adjust that in Excel or MATLAB or whatever you're using. We had these equations also, A equal Q over V. So since Q and V are the same for all the segments, that would not change, but B will change because B is QCA plus S over V, volume. CA is the same, Q is the same, but S will change with each segment, so that will change. And then CSS was B over A. That will change because B changes. So CSS will also change with each segment. So solve this for C of t, do a little bit of algebra. Within one of these segments, CSS minus C naught, which will also change when you change a different segment, e to the negative AT. And at the beginning of each segment, you have to adjust your time to reset to 0 at beginning of a new segment. And you have to recalculate your CSS and your C naught. Now, I actually do this a little bit differently in Excel. I increment at some interval delta t, and I set C of 0 equal the previous time step each time. So what I do is at time t, I set C0 equal C at the previous time step. And then I march to t and then repeat to t plus delta t, and then I repeat to t plus 2 delta t. So my time here this variable t is always going to be delta t for each step. So I'm doing piecewise with some small delta t rather than just doing it for the whole segment. I could jump right from 0 to 10 minutes, find the C there, and then jump to 20 minutes, and then jump to 30 minutes. But since I'm plotting it, I'm going to do that for a small time step. So you can do it however you want, but that's how I chose to do this. And so let's plot the source, this number of smokers. S is proportional to number of smokers by that 1100 times number of smokers. So I'm not actually plotting S, I'm plotting number of smokers as a function of time. If you look at the table, we have 2 smokers the first 10 minutes, 4 smokers the second 10 minutes, 0, etc. And so plotting that, this is what our source will look like. 2, and then it jumps up to 4 for the next 10 minutes. Then it drops down to 0. The next 10 minutes till 30 minutes has gone by. Then it jumps all the way up to 6. And then it drops down to 4 for the next 10 minutes. And at 50 minutes, nobody smokes from then on. Our source will look proportional to that. There's an Excel spreadsheet. Here's some screenshots from it, my solution. And you can see how I specified the volume flow rate, the volume. I specified S per cigarette, that's that 1100 microgram per minute per cigarette. C naught, CA. I specified a delta T of 1 minute. And then I use this modified version, as I said, where I reset that C0 each time. This goes on, but I can show you that the first 10 minutes had 2 smokers. So this is our segment 1. And then segment 2 starts right after 10 minutes, and that has 4 smokers now instead of 2. So my S goes to 4,400 instead of 2,200. Volume, Q, and CA are constant the rest of the way. And then for each segment, I calculate A, I calculate B, I calculate CSS. But starting here, I use that exponential equation, and then this is what I'm plotting. And at each 10 minutes, I change S, nothing else. Once I did this, I just filled everything down. All I changed was number of smokers. If I'm at this time step, I would set this as my C naught for the next time step, etc. That's how I did that. General case. What I'm going to do is take the file that we had last time when I did that simple smoke ventilation case. Remember, we had smoke in a hotel room. The firemen had to wait about a half hour to come in before the concentration went below a level that they could tolerate. I'm going to take that same one and just modify it. This is the unmodified case from last time. And you could see that B equal QCA plus S over V. And it's a constant here in this previous example. And I plotted C versus time, and you see it's a nice exponential decay. Now, let's model an unsteady periodic source. So instead of S being a constant, we have S being a function of time. Now, when S is a function of time, B will be a function of time as well, because B is QCA plus S over V. QCA and V are all constant, but S will be changing. So when S is not a constant, B will not be a constant either. And I'm going to modify this with a periodic S. And I just made up some numbers here. So there's a certain period and a certain amplitude of this source strength. Here's the modified Excel file. Notice that B equal, again, QCA plus S over V. And since S is not a constant, B is not a constant anymore. It's sinusoidal. And then the rest of this is all the Runge-Kutta stuff that I showed you before. And the result is, since I put a periodic source, I get some wiggles. And it actually, because of the way this source is, the source doesn't go to 0. It keeps oscillating forever. So it reaches kind of a steady state value that has fluctuations on it. So it's an oscillatory state. When it finally settles down, it's periodic. Now let's do another example. This is one that we had fun with. We called this the clever outdoorsman. Man sleeps overnight in a cabin with a volume of air in the cabin. The rate of fresh air in the cabin is 0.3 air changes per hour. Concentration of CO in the fresh air is some small amount. He has a kerosene space heater that emits carbon monoxide according to a periodic function, and that's milligrams of CO per hour. T is in hours here, not minutes. I want to calculate the concentration of CO in the cabin as a function of time. This is very similar to the previous problem. Q is equal to Q over volume times volume. And recall, this is how we defined the number of room air changes per hour. So this is equal to N times V. Our Q is 0.30. You can call this room per hour. It's really 1 over hour, but room is a non-dimensional quantity. It's not really a unit, but we have 32.65 meters cubed per room, if you want to think of it that way. So this gives me a flow rate of incoming air of 9.795 meter cubed per hour. At T equals 0, we have no heater yet. So he comes into this cabin and he hasn't turned on this kerosene heater yet. So C of 0 is equal to Ca, of course. So there's some carbon monoxide just in the outside air. And that is 10 ppm or 11.4 milligram per meter cubed. I solved this in both MATLAB and Excel. We'll put those also on Canvas. I made S as a function of time, a periodic function, just like the previous example. The bottom line is that YCO is 130 ppm and oscillates around this after a significant amount of time. And CCO turns out to be about 150 milligram per meter cubed and oscillates. I use ppm because I want to compare. This is the plot for carbon monoxide. This time I did it a little bit different. I added a separate column for S in milligram per hour, and that's where I put the sine wave function. A, Q over V is constant. B will change again because B is a function of S, and then the rest of this is all the Runge-Kutta stuff. And this is my CJ that I will plot against time. Over an 8-hour period, it levels off. This is 150 milligram per meter cubed, which is the average, but it'll just keep oscillating over that value. I also did this in MATLAB, and here's the plot in MATLAB.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.